Night settles over the Ural foothills. The wind is thin and cold, the kind that bites through wool coats and stings the eyes. Half a dozen men stand in a rough semicircle around a small, blunt-nosed aircraft painted the color of winter sky. Its wings are stubs. Its cockpit canopy is fogging with the breath of a pilot tightening his harness. There is no propeller. There is only a metal tube behind the cockpit, plumbed with pipes and tanks, waiting for a volatile marriage of oxidizer and fuel. This is the BI, Blizhny Istrabito, the close-range interceptor, conceived at terrifying speed in the first summer of the war. Tonight, in the spring of 1942, it will try something no Soviet aircraft has ever done before: lift from the ground under sheer rocket thrust. The pilot glances once more at the ground crew. A hand chops the air. Valves open. The engine coughs, then howls. Raw, chemical fire. The aircraft lunges. In seconds, it is only a sketch against the low clouds, accelerating toward a frontier of air where few pilots have ever flown, and where the rules are changing. The story of the BI rocket interceptor begins before that night run, in the uneasy months just before invasion. In Moscow, at a design bureau known as OKB 293, Engineer Commander Viktor Bolkhovitinov had gathered a small team obsessed with speed. Aleksandr Bereznyak, a young designer with a talent for simple, sturdy airframes, and Aleksei Isaev, a propulsion engineer who would later become one of the fathers of Soviet rocket engines. Their idea, first a whisper and then a plan, was to build an interceptor that could leap like a thrown knife, climb fast, strike at bombers threatening key targets, and return before its short-lived engine drained the tanks dry. On 22 June 1941, the Wehrmacht crossed the border. 8 days later, urgency hardened the idea into an order. The interceptor would be small, simple, and powered by a liquid-fueled rocket motor. Pumps were scarce, precision machining scarcer. The solution Isaev pushed, pressurized tanks driving propellant directly into the combustion chamber, was inelegant but fast to build. The aircraft's code letters, BI, were officially for close-range fighter, but everyone knew they also meant Bereznyak and Isaev. The propellants themselves were unforgiving: kerosene for fuel and a fuming nitric acid oxidizer that would burn through cloth and flesh. The engine, developed in parallel under Leonid Dushkin's leadership, promised up to around 1,100 kilograms of thrust. On paper, the BI could claw skyward at a rate piston engine fighters could not match. In practice, the engine would define everything about the aircraft: its frightening acceleration, its brutally short endurance, minutes, not hours, and a flight envelope that pressed against the unknowns of transonic aerodynamics. By late summer 1941, as factories evacuated east, the first airframes were ready for gliding trials. Without the rocket, towed into the air and released, the BI revealed itself as stable enough to fly, but different. A stubby fuselage and tiny wing area made for quick responses and sharp stalls. The team refined the controls, toughened the gear, and pushed forward. The plan was audacious: hand-build a squadron of rocket interceptors to defend critical nodes, industrial plants, transport junctions, where a sprinting defense could mean survival. In the chaotic months that followed, the program fractured and reformed among trainloads of crates heading for the Urals. Test sites changed. Airframes were cannibalized to keep the most promising holes alive. Ground tests of the engine were violent affairs. Metal buckling, seals failing, fire licking along the floor. But each failure taught something. Each repair brought the day closer when pilot and engine would be united in the air. That day came in May 1942. The pilot chosen for the first powered flight was Grigory Bakhchivandzhi, a test aviator with a calm, unflinching manner. He strapped in, took the weight of the unfamiliar machine, and lit the engine. The BI surged forward, rose cleanly, and howled into the sky. It did not last long. No rocket flight would. But it was enough. Enough to prove that a short-range interceptor, born of chemistry rather than combustion pistons, could fly under its own power. It was a moment of vindication for engineers who had slept on shop floors and signed their names beneath promises they weren't sure they could keep. In the months that followed, the team built and modified a handful of prototypes: BI-1, BI-2, BI-3, and others, experimenting with landing gear, wheels on early frames, landing skids on later ones, fuel lines, and control surfaces. The airframes were tiny, roughly 6.5 meters in length, a wing just over 6 meters tip to tip, an area so small that high speed came quickly, and a misjudged pull could bring the wing to the edge of lift in an instant. The planned armament, 2 20mm Shavak cannons in the nose, was straightforward, but weight and vibration were enemies in a machine that lived on the margins. Test aircraft flew unarmed to preserve performance and eliminate variables. Pilots began to describe the sensation of flying the BI with a mix of fear and delight. One is said to have likened it to a devil riding a broom, a metaphor for the way acceleration pinned you, the way the aircraft leapt like a striking animal when the throttle opened. In level flight at lower altitudes, the BI could reach speeds that piston fighters struggled to match. Its climb rate was extraordinary for its day. And then, abruptly, the engine would wind down, and the pilot would be left with a powerless dart, gliding down to land on wheels or skid, managing energy with a surgeon's precision. A miscalculation at that point meant running out of sky. All the while, engineers wrestled with the unknown. The world's aerodynamicists were discovering that as an aircraft approached the speed of sound, the flow over wings and tail transformed. Local regions went supersonic, shock waves formed, and the center of pressure shifted aft. The term Mach tuck did not yet circulate in Soviet test rooms. The phenomenon itself did. In the BI, as speed climbed, the nose wanted to drop. Elevator authority, how much the tail could fight that pitch down, was finite. The little interceptor was faster than the language available to describe its behavior. By early 1943, winter hard on the ground, the program had logged a handful of powered flights and many more gliding tests. Engineers adjusted the tailplane incidence, tweaked control linkages, and debated whether the problem was aerodynamic, structural, or the human factor of a pilot reacting to a new regime of forces. Decision points loomed. If the BI could be tamed, if the landing skid configuration worked, if armament and sighting were integrated cleanly, it might be produced in small numbers for point defense. Plans even circulated for an attack variant that could carry light bombs into a concentrated strike. Those plans remained conceptual, shadows of a future that never fully formed. On 27 March 1943, Bakhchivandzhi climbed into the cockpit again. The test card called for a controlled acceleration run to explore the high-speed behavior that had begun to worry the team. The weather was fair, the air was hard and cold. He lit the engine and the aircraft surged off the strip, climbing rapidly. Ground observers tracked the tiny shape as it leveled, then descended gently to build speed. Seconds ticked. The sound changed, a sharper whistle at the edge of the engine's note. At roughly a minute and a quarter after takeoff, 78 seconds by post-flight reconstruction, the aircraft pitched down into a steep, uncommanded dive. It struck a frozen lake beyond the field. The impact was devastating. There was no chance for survival. Shock rippled through the team. A quiet pilot, well respected, an aircraft that had tested the limits of what anyone in the Soviet Union had yet tried to fly. The official inquiry considered multiple hypotheses. Some engineers believed the rocket shut down abruptly, causing a surge of deceleration that threw the pilot forward and interfered with control. Others pointed to the growing suspicion that high-speed compressibility effects were overpowering the tail. At the time, the evidence was incomplete. Wind tunnel testing robust enough to settle the question would only come years later. When those tests were finally run, they confirmed what many had come to suspect. As speed approached the transonic, the BI's nose-down tendency, Mach tuck, grew rapidly, and the elevator could not generate sufficient countermoment. An aircraft that was well-mannered at 500 or 600 kilometers per hour could become a predator at 800. Bakhchivandzhi's death changed the tone of the program. The Air Force had tolerated the risks of experimentation while the possibility of a miracle weapon remained alive. Now, with resources tight, conventional fighters improving, and jet turbine research emerging from laboratories, the strategic argument for a short-range rocket interceptor was harder to make. Test flying continued in cautious steps with other prototypes and pilots, but the aura of inevitability had gone. The BI was never deployed to a frontline regiment. No bomber stream ever met its abrupt acceleration over a defended factory. No Luftwaffe pilot ever saw its Stinger nose flash across his canopy and wondered what powered this strange propellerless thing. As 1943 turned into 1944, the rocket interceptor's moment passed. The workbenches at OKB-293 were filled with other projects. Some engineers moved on to programs that would define the post-war years. What remains, then, is a paradox. The BI-1 was both a technological dead end and a pathfinder. As an interceptor concept, its endurance was simply too short. On a typical engine load, a BI flight might last 2, 3, perhaps 4 minutes of powered time. That was enough to scramble, climb, and fire a short burst, if the target was already nearby. It was not enough to patrol, to vector, to respond flexibly as a tactical situation unfolded. In war, endurance is as much a weapon as speed. But as a research aircraft, whether or not it was labeled that way at the time, the BI cracked open doors. It forced pilots and engineers to grapple with compressibility, with control authority at high speed, with new failure modes. It seeded a generation of minds with data and experience that would pay off later in the Soviet Union's ambitious flight programs. And it told those minds something visceral about the cost of pushing the envelope too far, too fast. Consider the pilot's experience. In a piston fighter, power built gradually. Torque, prop wash, the rhythm of engine and propeller, these were cues a pilot could ride. In the BI, power arrived like a detonation of intent. The moment the rocket lit, the aircraft stopped being a machine and became a trajectory. Airspeeds leapt, altitudes scrolled. The engine drank itself toward silence. Then the pilot switched mental modes, became a glider pilot in an instant, nursing energy to a landing on a bare strip or a snow-covered field. It took a kind of dual consciousness rare even among test crews, the ability to live inside acceleration and then inside quiet, with no time between. Engineers, too, learned to live in two worlds. They worked with materials and fluids that punished error. Red fuming nitric acid is not a forgiving colleague. And they worked with equations that were, at the time, only partially tested. They sleeved valves with whatever alloys they could find, soldered and resoldered joints, and built pressure vessels strong enough to feed a hungry chamber without exploding. In the morning, they might be chemists, in the afternoon, aerodynamicists, and at midnight, machinists. Their project was small by the vast metrics of war, but it carried a heady sense that a frontier was near. Across the front lines, Germany was developing its own rocket interceptor, the Messerschmitt Me-163 Comet. That program reached combat and revealed its own contradictions. Meteoric climbs, terrifying handling near landing, fatal accidents. The Comet shot down Allied bombers, but at a loss rate that often made the victories feel Pyrrhic. In both countries, rocket interceptors proved one thing clearly: raw speed alone was not enough. What fighters needed were efficient power plants that could deliver high speed and usable range together. The answer, almost everywhere, would be the turbojet. In the Soviet Union, the lessons from the BI era flowed into work that within a few post-war years put jet fighters over parade routes and frontiers. Some of the engineers who had nursed those early rocket lines became key figures in a new propulsion epoch. Aleksei Isaev, in particular, channeled his experience with temperamental small engines into robust designs for missiles and spacecraft that would carry cosmonauts beyond the sky. In this sense, the BI's heritage is not measured in air victories, but in trajectories that reach far beyond the atmosphere. And yet, the BI remains a story of people, of Bakhchivandzhi, remembered by colleagues as disciplined and modest, who took a machine to the edge of what it could do and crossed a line no one could see. Of ground crews who handled tanks of chemicals with care sharpened by fear, their gloves crisping when a drop splashed wrong. Of young engineers learning on the job and leaving notebooks filled with calculations in a script smudged by long nights. In later interviews, some of them recalled the mix of pride and dread they felt watching the little interceptor launch. Pride in the proof of concept, dread in the awareness that their math might have missed a term no one yet knew how to calculate. There are also the absences in the record that a responsible historian must address. The exact top speed achieved on that final March flight is not definitively known. Surviving accounts suggest a range approaching the transonic, and some figures cite 800 to 900 kilometers per hour. This should be treated as estimated. Likewise, while wind tunnel work conducted after the war strongly supports compressibility-induced pitchdown, Mach tuck, as the principal cause of the fatal dive, early speculation about pilot incapacitation due to sudden deceleration cannot be entirely dismissed, without contemporaneous cockpit telemetry, which did not exist. That early hypothesis remains contested, though it has lost favor. The precise number of prototypes constructed, often given as 9, covers airframes in various states of completion and modification. It is accurate enough to say a handful, with several flown and others used for static testing and parts. There were plans, too, that never matured. Drawings and memos reference a variant intended to deliver small bombs in a point strike. Another idea aimed to refine the landing gear for rough field operations, moving fully to skid landings to reduce complexity. These too should be marked as contested in their details. Wartime programs leave trails of paper more aspirational than actual, and what one office envisioned sometimes died in another's in-basket under the weight of shifting priorities. By early 1945, the BI program quietly closed. The war was turning, then ending. Jet engines, copied, acquired, or rapidly developed, promised more practical paths to speed. On factory floors, workers unbolted jigs and moved them to corners. Airframes that had strained toward a rocket future were pushed to the back of hangars, their skins dusty, their tire treads fading into the concrete. A few survived into museums and photographs. Odd, compact, fierce-looking machines that invite a double take. They look like toys until you stand close and imagine the scream of the engine and the taste of nitric acid in the air. What should we take from the BI's short life? First, that desperation in war produces inventions that are both brilliant and brittle. The BI solved the problem it chose to solve: rapid climb and dash interception, at the cost of everything else. Second, that gathering empirical knowledge at the edge is costly but essential. The men who watched shock-induced pitchdown ruin a flight were witnessing the future of flight dynamics announce itself in the starkest way. Third, that technology's human dimension is inseparable from its statistics. A graph of speed versus time cannot contain the image of a pilot's hands tightening on a control column that is suddenly too light, then too heavy, or the quiet in the control room as dots on a plotting board merge. And finally, that not all weapons are for war. Some are for learning. The BI-1 never defended a factory, never met a formation of German bombers over the Urals, but it helped teach a generation how to live in fast air and how to build engines that would carry vehicles higher and farther than any airplane built for battle. In that sense, the little Interceptor flew not just too close to the edge, as the metaphor goes, but exactly where it needed to fly to show where the edge was. We end where we began, in the cold dark of a Ural night. A pilot decisive on the throttle, an aircraft swallowing distance, a team straining to read the behavior of a machine faster than their words for it. The glow of the exhaust becomes a star, then a line, then nothing. Minutes later, if all goes well, skids or wheels hiss against snow or earth, and men run out to meet the pilot. They speak quickly, excited. He writes numbers in a notebook. They argue quietly about a tremor felt at high speed, about a hint of nose drop, about the right angle of incidence. They go back to the hangar. They solder and file and argue again. History often celebrates what works, but progress, in the end, is a ledger of attempts. The BI-1 was one of those attempts, brief, dangerous, unforgettable. It left behind a pattern in the sky that others would follow, with safer, longer-legged engines, and it left behind a set of cautions that engineers would carry into every new design. If you listen for it, you can still hear the sudden, ragged howl of its rocket lighting in the dark, the sound of a door opening onto a new era, and the cold wind that rushed in.